Hello there, this is exercise 4D. We're looking again at vectors, and we're looking now at the distances between a variety of different problems, lines and planes basically. So I'm going to crack on with this because there's quite a lot to get through. Now the shortest distance then from a point to a plane, obviously on my picture here I've got a point up here which is M, and that point M, and we're basically wondering how far away it is from the plane, and the shortest distance is always at right angles. So that's why this is at right angles, and therefore we're interested in the normal. That is the normal vector, which is shown over here. Now look, there's two things I'm going to do. I'm going to basically try to use a bit of common sense and show that this formula is right. This formula is given to you in the formula book, so you are almost expected to use it, but I'm going to show you this in two ways. Let's have a look at this in an example question then. So applying this equation 2x, straight away I want to write that as a r dot n scenario, and there is a plane, isn't it? A plane has that equation. So r dot 2, 2 and minus 1 is equal to 11. That's my plane. A line is perpendicular to the plane and passes through the point. So we are in that situation when we've got a plane, we've got this point in the plane, and we've got this point above the plane, which I'm going to call M, and that's the distance I'm trying to find. This is called P. I can see it here. So find the equation of the line. Well, presumably they mean this line here all the way through. Now to get that, I need the direction of that line. Now the great thing is the direction is the normal. So that's equal to 2, 2 and minus 1. And then I just want a point on the line. Well, I've got a point on the line, it's M. So I reckon R equals it's a point on the line, which is minus 3 and 4 plus lambda times by the direction 2, 2 minus 1. So that's the first one bit done. Now part 2 says find the coordinates of the point P where the line intersects the plane. Now, well, we saw this last time actually, didn't we? So to find where that intersects the plane, you substitute this line into my equation for the plane and see what lambda is. So part 2 then is basically we go, rather than r, we write this thing. So I've got minus 3 plus 2 lambda, minus 3 plus 2 lambda, and what's that, 4 minus lambda. And I've got to dot that with the normal vector, 2, 2 minus 1. 2, 2 minus 1, and they tell me it's equal to 11. So I can just multiply that out. So that gives me minus 3 times 2 is minus 6 plus 4 lambda. And the next row actually gives me exactly the same thing, minus 6 plus 4 lambda. A difficult one is, not difficult, but different one, minus 4. The row equals minus 4 plus a lambda, and that is equal to 11. So how many lambdas I've got? 4, 8, I've got 9 lambda, minus 12, minus 16, move that over equals 27. So therefore lambda equals 3. And if lambda equals 3, presumably I can chuck lambda equals 3 into this, minus 3 plus 6. So that's my point P then is 3. The second one must be the same because it's got exactly the same formula. 4 plus 3 lots of minus 1, I think that's 1. So I've written it as technically a direction vector, but P is therefore 3, 3 and 1. Let's check those two before I go on. So I've got 3, 3, 1 and that formula. Can we see it? 3, 3, 1, we can see it. So we've done that bit right. I only did that because I was running out of space already. So I erase all the ink on that slide. Now, from the shortest distance, find the shortest distance from M to this point of intersection. Well, actually, what did we say it was? We said it was 3, 3, 1 we just found. So we've got that point is 3, 3, 1. Now remember my picture was basically it was above the line. And we had a point M, we had a point P, and we had this line in between. Now that just looks like Pythagoras' theorem to me. I can just do M is minus 3, and 4. And therefore MP is the distance between them. It's the square root of, they're 6 apart, so it's 6 squared, plus they're also 6 apart, so 6 squared, and these are 3 apart, so 3 squared. So that's root 7 2 plus 9, that's root 81, which is worked out perfectly as 9. And I did actually see the answer as 9 at the bottom here. Now, of course, what it wants me to do is to check my answer using the formula. So this is the bit I've not shown you yet. And this is the bit I want you to see. So to get this, what I basically do is I can use the position vector, which this point gives me. This B actually is meant to be, oops, I haven't got my pen. This B is actually the position vector of this. So I can basically go, my B is my really what they've called M. So I use that point and I dot it with my N for my plane, 2, 2, and minus 1. What's that give me? It gives me minus 6, minus 6, minus 4, which is minus 16. And it does say then take away P, and P is the, if you looked at our description before, is actually this 11. So what I've got to do therefore is I'm going to write B dot N minus my P equals minus 16 and minus that 11, which of course gives me minus 27. So I've got to know what all these different bits stand for. And it does say ignore the magnitude of it, or the minus sign of it. So my final line is D equals, well, it's that 27, ignore the minus. Oh, I've still got to work out the normal. So if I do magnitude of the normal, the square root of 2 squared, which is 4 plus 1, that's actually 9. It's got to be square rooted, so really that's 3. So 27 over 3 is 9. And of course, that's what I got before. So it highlights the fact that these formulas work, and we can basically use them in the exam. There's the 9 again for confirmation. Here's another example, almost identical. So I've got a point here. So the very first thing I can do is use the 2 minus 2 for the point, what they've called the B. I dot it with my normal, which is this 2, 1 and minus 3, and I see what I get. Oh, actually, it also says minus the P, so I might as well do it at the same time. Minus the P. The P is this 4 here. So let's do that. 4, I get minus 2, I get minus 12, and don't forget this minus 4 as well. Oh, so they effectively cancel. I get minus 14 for the top line. I need the magnitude of the normal, which is the square root of this thing here, which is 4 plus 1 plus 9 when you square them all, which is root 14. All right, 514, yes it is. So I can ignore the minus, so my D distance is 14 divided by root 14, which is root 14. Let's see if that's the answer. Root 14 is the answer. They've got their working out there. So that you can see that was so much quicker. So we like that. Now the shortest distance between two skew lines then, it gives me the formula again. So this again is in the formula book. So I'm not going to justify it this time. I'm just going to show you it in action. And let's get it going with an example. So what we've got, well, first of all, I need to write this as a equations of two lines. So I don't like the fact they've done it like this. I think it'd be useful if I was able to write this one as R. And I want you to check this. I did this one earlier. I got 1 minus 1 minus 2 plus lambda. And I got 2, 1, 1. So that's the first line. And my second line, when I rejigged it about, and of course we've done this already, this is something we can do. I think that's a 7. 3 minus 2, 7. Plus mu of 1 minus 2 and 3. Now once you've got that, you can then find out your normal vector. And of course we can do the normal vector when we use the two direction vectors here. And my normal vector is this IJK trick that we've seen before when we cross product them. And so I'm going to write 2, 1, 1 and 1 minus 2 and 3. And again, because I'm short of time on this video, I'm just going to tell you that. But again, you can check it. And I suggest you pause your video and see if you can get the same as me. I actually got, when I did it, 5 minus 5 and minus 5. And immediately I got that. I thought, oh, 5's going to all of them. So therefore I wrote the normal vector as 1 minus 1 and minus 1. Now, notice what I've got then. I now have my my n, if you like. And therefore it allows me to do all that. Now, the other thing that I need is 2 points on the lines. So that's my B and my A. And I get that from these points here. So I've got my A, there's my A, and here's my B. So if I do as they've said, take away b minus a, and then it wants me to dot it with n. So what is my b minus a? It's 3 minus 1 is 2. Minus 2 minus minus 1 is, I think, minus 1. And 7 minus, that's 9. And I'm going to dot that with the n, which is 1 minus 1 minus 1, which gives me 2 plus 1 minus 9, which sounds to me like minus 6. Now, of course, it does say ignore the minus magnitude, or I need the magnitude of n, which is, if you do the magnitude of n, you quickly realize it's root 3. So this distance then, my distance here now is 6 divided by root 3. If you type that into your calculator, you get 2 root 3. That was quick for me to do there because I did a lot of the work in advance. But so this next one I want us to do is also in the formula, and it says the shortest distance of a point from a line. And they're interesting. This is a 2D line. I know it's 2D line because it only gives me an x and a y bits of information. So it's 2D lines, and it's in our formula book. So let's have an example, and we can jump straight into it. And our example is a line passing through this pair of points. So our first thing I want to do is I'm going to find the gradient between them. 9 take away 5 is 4. 1 take away a minus 2 is 3. So I now know the gradient of my line is 4/3, and using this standard sort of maths from year 12 formula, I can find the equation of this line. Pick either, I'm going to use the 1, 9 because they're nicer numbers. So y minus the 9 equals 4/3 x minus that 1. Move the 3 over to the other side, I get 3y minus 27 equals 4x minus 4. And they want me to write it in this ax plus by equals c. That's the form I want, ax plus by equals c. So I might as well move them over. In fact, I'll move it that way. I've got 4x minus 3y. And I reckon that's equal to minus 23. So that's my equation. And it says here, in order to find this distance, I substitute my point. And I'm then able to find the shortest distance between this line and this point. And so I do it by going ax plus by minus c, where I sub it in. So my a is 4, and it's times by minus 4. My b is minus 3, and I times it by my 7. It then says minus my c. What was my c? It was minus 23, or plus 23, I think. So what do I get? I get minus 16, minus 21, plus 23. So minus 37. I reckon that's minus 14. A lot of 14s flying around here. And what do I do with that? I divide it by the square root of the a squared plus. All right, so I go 4 squared plus the 3 squared. Square root, which is obviously 5. And it again says ignore the minuses, so this distance I think is 14/5. So that's the only example 14/5. That's the only example you're seeing of that. Now I should point out that I'm going to save this one for the lesson, and that's because it's not actually in the formula book, and it's quite a long-winded procedure. You'll notice something here. It's basically we'd use this when we've got the distance between two parallel lines. So we've got parallel lines, obviously the direction of them is presumably the same, otherwise they're not parallel. And it's written then r is a plus lambda d. So this is, because I've got an a here, this is my a plus lambda d. And my second line is also with a d, it's r equals b plus mu d. And obviously, I'm going to be told somehow these 2 points here. I say obviously, I know we are because the formula talks about the points A and B. So we're going to be told those 2 points. And effectively, we find the angle theta here. We find it using this formula here, the cos theta formula. That allows me to go, therefore theta equals whatever. And then I can use this formula. I can find out what the distance is using this magnitude of a minus b sine theta. Now this is not in the formula book, so we are going to have to learn it. And in lesson then we'll go through that And there's an example of it in action, and we'll then look at exercise 4D. So thank you very much. I'll see you in class.